Okay, we're recording. Hi everyone, my name is Hayden Farriester and my partner is Ahmed Muqtadir. This project focuses on optimization techniques for a SerDes system operating at 28 gig and 56 gig data speeds. SerDes can be found in applications such as network switches or any other device that involves fast data communication. Now, what is SerDes? SerDes stands for serializer and deserializer. Here we have an electrical signal that is converted into a data bit, and then from the transceiver, it is then propagated across this channel, which can encounter discontinuities such as crosstalk, intersignal interference, or jitter. And then once the data signal makes its way to the receiver, it is then converted back into a data bit. Now, to begin our methodology, to apply optimization techniques for the discontinuities that may occur, we focus on SerDes characterization. That involves capturing measurements to understand SerDes performance. The measurements we captured are channel operating margin, bit error rate, which is this bathtub curve, the eye diagram, return loss, insertion loss, and pulse response. I'll now pass off to Muhammad.
Thank you, Hayden. So in our board, we had a very simple stack up of just a 10-layer board. And in this, we had our signal going from the top layer down to the third layer and back up to the top layer. So we also included crosstalk in our simulation, which is just when adjacent traces interfere with a given signal/channel. In ours, we had a total of 3 channels, which was 2 aggressors and 1 victim. We also had impedance difference via via. This is because all real systems will have some form of this. The goal was to see what amount of crosstalk and what channel length/losses are correctable using an eye diagram. Now, Hayden will talk about jitter.
Yes, to briefly talk about jitter, we focused on injecting jitter at the transmitter end, and this was based on duty cycle distortion, random jitter, and deterministic jitter. And then here we can enter in the amount of jitter we want to inject. And this helped us understand what amount of jitter is too much before the SerDes system fails. To discuss more about our analysis and results, we first focused on 28 gig NRZ modulation. NRZ stands for non-return to zero, and it shows 2 signal levels that represents bits of 0 and 1. To decide on the best parameters to achieve a COM above 3 dB, the channel length was swept. Based on simulations, 1/2 inch to 3 inch channel lengths resulted in low insertion loss and high return loss. Above 3 inch, the return loss was close to 0 dB and insertion loss was too high. To achieve an optimal eye height, we tune the FFE tap cursors to optimize the eye height and width. Tuning these settings also improves the COM. One observation we noticed is that overtuning the FFE can actually over-equalize the signal as shown here. I'll pass off to Muhammad to discuss PAM4.
Yes, so we use 56G PAM4, so pulse amplitude modulation, 4 level for the other simulation. And the reason it's 4 level is because it sends 2 bits of information per unit interval instead of 1. What this does is that allows for more information to be sent within the same time, but it also makes it more susceptible to intersymbol interference, ISI. So because of this, what we did is we simulated different channel lengths, the losses associated with them, and we saw how it affected our eye and how we can improve our TX equalization techniques. So what we saw from this simulation was that 56G or just PAM4 is more susceptible to TX equalization techniques versus 28G or NRZ. Next, we did crosstalk simulation. And what we did, as mentioned before, is that we had 2 aggressors and 1 victim. And what we saw was that when we ran for different channel lengths, we wanted to see how it would affect our SerDes performance. We also had impedance difference via via, which essentially just caused more reflections of our signal. So what we saw was that as we increased the channel length, the eye performance was completely closed, as we see in the first image on the top. And what we did is we changed our TX equalization techniques, and what we saw was improved results, which can be seen on the bottom. So in summary, we ran simulations for 28G NRZ and 56G PAM4 to see how different transmitted equalization techniques, channel lengths, and impedance differences would affect our jitter crosstalk, which in turn affected our SerDes performance. Thank you very much.